In the last couple of classes, we've learned about what stress is. Today, we're going to move on to a new topic called strain. If you've taken material science, you know these two are related, but let's quickly review the two kinds of stress that we've talked about. First up is normal stress. We use the Greek lowercase sigma for this. The units will be psi or pascals. And the picture that goes along with normal stress is if I had a bar that was being pulled on with a normal force N, and I cut it open to expose the surface to find the internal force. I divide it then by the area, and this is my normal stress, pulling out and away if it's in tension. So that is my normal stress sigma. It's equal to N over A. The other stress was called shear stress. Shear stress is a lowercase Greek letter tau. Same units, also psi or pascals. Think of this as like a little cube of material that is being sheared by a pair of equal and opposite forces. V, like that. So if you were to cut this open and actually look at that surface area that's being sheared with the force V, the shear stress is going to be spread out somehow parallel to the surface. So how the normal stress was perpendicular to the surface coming out and away, the shear stress is in that same plane with the surface. And so far, all we've learned how to calculate is average shear stress, and that we find by taking the shear force divided by that area that it acts over. Let me just shade the areas in. Both of these have to do with how big is the load that's acting on this. So this is related to the actual loads or forces. Strain is something different. Just like with stress, we are also going to have a normal and a shear. The Greek letters we're going to use are a lowercase Greek letter epsilon and a lowercase Greek letter gamma. While the stress is related to the loads on an object, what the strain is related to is the deformation, also known as shape change, length change. So the idea here is that when a force is applied to an object, something happens to the object. It's going to cause a change in the size or shape. And it always does. Any force applied to any object will cause maybe a tiny change in shape or size, but there will always be a change in the size or shape. In statics, we assume that that's negligible. We treat everything like it's a rigid body and assume it's negligible. And it turns out that you can solve a lot of problems by assuming that that shape and size change is negligible. But at some point, you often do need to start to account for how much is the shape or size going to change. So if I pull on a bar, for example, what's going to happen to it is it's going to get longer, and it's also actually going to reduce the diameter just a little bit. The main change is going to be an elongation due to a tensile force. What if we had the same shape, but instead of pulling on it, we pushed on it, we compressed it? Well, we're going to get a little bit shorter from pushing it. And this is kind of hard to see with big structural things. You can see this a whole lot more easily if you grab, say, a rubber band and pull on it. You see that it gets longer. This is both going to be what we call a normal strain because they're caused by normal stresses. We're pulling or pushing on a bar, and so we're going to create a normal force in that bar. You divide that by area, you get normal stress, and that's going to be related to the normal strain. We can also have shear strain, and what that's going to look like is, again, think for shear like you originally had a cube of material. You're shearing it by applying a force left and right on the top and bottom. What's going to happen is it's going to end up distorted, kind of like that. What was a cube with 90-degree angles is now shifted off to one side because of the shear loading. So this shape change we call shear strain. All right, we need to be able to calculate this. Normal strain, let's do that one first. The way we calculate normal strain is we say that if you have a change in length of a bar and you divide it by the original length of the bar, we're going to call that normal strain. If this was my bar, just drawing it in 2D, and the length was L0 before you applied any load or any length change to it, then it's going to get a little bit longer or shorter, and we're going to measure that length change, delta L. And if you simply divide those two numbers by each other, you will get what we call normal strain. A positive normal strain means that you have an increase in length, and a negative normal strain means you have a decrease in length. This strain specifically is what we call engineering strain, and it's because we're dividing it by the original reference length. Engineering strain just means you are referencing your strain to the original length. There's another kind of strain you could calculate where instead of referencing it to the original length, you reference the length change to the new final length. We're not going to deal with that in this class because we're going to be dealing with very small strains in here. And so using the original length works great for the problems that we're going to be solving. What are the units of this thing? Remember how stress was PSI and Pascal? Well, can you see what's going to happen? We're going to have a change in length that would have units of inches or meters divided by an original length, also units of inches or meters. So we are going to say that this is dimensionless. Sometimes you will see it written as millimeters per millimeter or inches per inch. It's still dimensionless, but sometimes people call it that. So if you ever see it that way, you know it's just a strain unit. All right, let's talk about shear strain for a minute. What is shear strain? It is this Greek letter gamma, and we're going to define it as the change in angle from pi over 2. Remember, pi over 2 is 90 degrees, but we're going to specifically use radians in here. So the way we're going to calculate it is we're going to start with pi over 2 as kind of the original angle minus the new angle. So pi over 2 is the original angle, and theta prime is the new angle after shearing. So when you subtract these two, you're going to get a change in angle. As far as that theta prime goes, it must be in radians or this does not work. You don't want to take pi over 2 and subtract from it 86 degrees. We're going to call this shear strain dimensionless, although technically it's in radians, but we treat radians as being kind of our dimensionless angle. And then we're going to say that a positive shear strain means that it is a decrease in angle. Let me show a picture. Here is in 2 dimensions a square who originally has an angle of pi over 2 right there, 90-degree angle at that corner. So now we're going to experience some kind of shear, and it's going to become this little parallelogram that no longer has 90-degree corners. What I'm going to do is find the new angle. The new angle is going to be right here. This is my theta prime. That's the new angle. The original angle is pi over 2. There's my new angle. So what are we going to get when we subtract them? Gamma. It's going to be right here. So these gammas are going to be really small numbers. I drew this very exaggeratedly. It's not going to be like a pi over 6 kind of a number. You're going to get very, very small numbers because these are small angle changes. This one that I drew in the picture, this would be a picture illustrating positive shear because the angle was originally 90 degrees and now it is smaller than 90 degrees. So when you take pi over 2 and you subtract from it this new angle, you're going to get a positive number, and it's going to be this little angle, and it means that it's sheared kind of off this direction. If it had gone the other direction, the new angle would be bigger than pi over 2, so when you subtract it from pi over 2, you will get a negative, and your shear strain might be over this direction, and it indicates that it's sheared to the left instead of to the right. So there's our definition of shear strain. We have our definition of normal strain. I've got 3 examples to go through with you today. Here's example 1. We have a bar. It is pinned at A. It is held up by a couple of cables. It has a length of 7 meters, and these cables have lengths of 4 meters, and someone's applying a force P out here. So if we wanted to solve this as a statics problem, we'd draw a free body diagram. We'd have a tension in this cable, tension in that cable, an AX and an AY. You'd quickly figure out you actually can't solve for 4 unknowns in a 2D problem like this. It's not a statics problem. We're not going to draw a free body diagram because look what the question's asking. Question tells us that P is just big enough to cause this bar to rotate downward so that C moves downward 10 millimeters. And they want us to find the normal strain in wire CE as well as wire BD. Here's why I'm not going to draw a free body diagram. The problem doesn't ask us to find forces, and the problem doesn't ask us to find stresses, which means I probably never need to find any forces at any point. Instead, I'm going to use the geometry. How long is this? How long is that? How long is that? The fact that it's pinned at A, so it's going to need to rotate downward. I'm probably going to draw a triangle here and find the length change or the displacement of point B. And then normal strain, I just need change in length divided by original length. I just mentioned geometry. I start with the bar originally going from A to B 3 meters over to C another 4 meters over. It's going to tilt downward. And I'm going to say that 10 millimeters is pretty small compared to 4 meters. So it probably doesn't matter if you treat C as going straight down versus rotating back a little bit. And the same thing with B. Let's make our life easy and just treat it like it moves straight down. I know that side of that triangle is 10 millimeters. I know the whole thing is 7 meters, and this part is 3 meters. So what I want to try to find is going to be the deflection of B. Why don't we use similar triangles and figure out how big the deflection of B is going to be? So I'm going to take this side relative to that side. It's got to be exactly equal to this side relative to that side. I'm quite literally using the tangent of this angle and saying that the tangent of that angle has got to be the same in both cases. I have got delta B is to 3 meters as delta C, 10 millimeters, is to 7 meters. If you want to convert those all into millimeters, you can, but notice that those meters are going to cancel out and we'll get delta B in millimeters. Doing that, we get delta B comes out to be 4.29 millimeters, which should make sense. It should be less than 10 millimeters, and it is. So now let's go find those strains. We know the strain in BD is going to be the change in length divided by the original length. Change in length is just that 4.29 millimeters that I just found. And the original length, now I'm going to have to put this in millimeters. Original length was 4 meters. So divide by 4 meters, well, in millimeters, that would be 4,000 millimeters. And we should get a small number. We do. We get 0.00107. Next, we need to find the strain in CE. It's also delta L divided by L0. This one we were given, the change in length is 10 millimeters, and the original length is also 4 meters or 4,000 millimeters. You get 0.025. Exactly. If you want to put another 0 so that it's 3 sig figs, you can. And we found the normal strain in those 2 wires. No free body diagram necessary, but we did need this other geometric diagram just to help us recognize a similar triangle so we could figure out delta B. Let's do one with shear. This is kind of a complicated problem. Let me talk you through the picture first. So what we have is a square of material. This is supposed to be an actual perfect square so that all of those corners, A, B, C, and D, are all 90-degree angles. And then what happens is because of the loading applied to this chunk of material, point D moves in by 0.3 inches. Point B also moves in by 0.3 inches. Point C moves down. So we're going from the solid black was the original shape. The dashed blue is the new shape. So point C moves down by 0.2 inches and point A moves up by 0.2 inches. And then we are asked to find shear strain at corner A and at corner B. We're also supposed to find the normal strain along line AB, line AC, that's all the way across this way, and along DB that way. And this is really a geometry trig problem. I actually found this problem easiest to do by just zooming in on a triangle. So right here, we had an original triangle that was actually a 45, 45, 90 triangle. And then what happened is we end up with this deformed triangle right here. So let me color that in a different color. I'm going to make this my purple triangle, and we're going to find out everything about the purple triangle and then use that to help us get some of those strains. What do I know about the purple triangle? Well, I know this vertical side right here, it's 10 inches plus 0.2. And this side is 10 inches minus 0.3 inches. So I know these two sides. I should be able to use that to figure out, say, this angle and maybe that angle. I called this one up here theta 1. To find theta 1, I'm just going to use the fact that the tangent of theta 1 is the opposite side. Well, that was the 10 inches minus 0.3. So the opposite side should be 9.7 inches divided by the adjacent side, 10.2 inches. And we can solve for theta 1. I did this, and I'm just going to write it down in degrees so that you can see that it makes sense because my brain thinks in degrees, not radians. Theta 1 came out to be 43.56 degrees, but we're going to want it in radians. That is equal to 0.7603 radians. Make sure you keep a bunch of decimals with your radians. And that should make sense, right? It looks like the original angle was 45 degrees. The new angle is a little bit smaller than 45 degrees. Now we can actually find the shear strain at A. Do you see how we can find that out? The original angle at A was this whole 90-degree angle. To do this, I actually need the new angle at A. Can you see that that's going to be 2 theta 1? The new, we called it theta prime at A, is going to be 2 of those theta 1s, which comes out to be 1.521 radians. So that's theta A prime. That's the angle right up here. So now we can find gamma at A. The shear strain at A is pi over 2 minus the new angle at A, theta prime A which is the 1.521 I just found. Subtracting those two numbers, you get 0.0502. And it comes out as a positive because the new angle at A is smaller than pi over 2. So when you subtract from pi over 2, you get a positive. Let's do another triangle, an orange triangle over here, because it specifically asks for the shear strain at B. So let's do a triangle that actually includes B. And what I want to do is actually find the angle down here. We'll call it theta 2 that's next to B. The tangent of theta 2 is going to be 10.2 inches divided by 9.7 inches. So theta 2 comes out to be a little bigger than 45 degrees. Comes out to be 46.44 degrees, or 0.810 radians. All right, so then the theta b prime, the new total angle at B, and here is going to be two of those. So theta prime b is 2 theta 2. Multiplying that out, I get 1.62 radians. So gamma b is pi over 2 minus that new angle at B, theta b prime. It comes out to be minus 0.0502. All right, it is not a coincidence that these two are equal and opposite. It shouldn't be surprising this came out as a negative, because you can see that at B we started with a 90-degree angle, and because of the change of shape we now have an angle that is bigger than 90 degrees. Okay, so we get exactly the same number, but we get the positive up here at A because that's the angle that got smaller, and the negative down here at B because that's the angle that got bigger. All right, shear strain done. Now let's go do normal strain. So along AB, what I need to do is I need to find the original length and probably find the final length so that I can find the change of length. So for normal strain, we need the original length of AB. Use a 0 for that. Well, that's going to be square root of 10 squared plus 10 squared. It's using that triangle. This side was 10 inches, this side was 10 inches, so that hypotenuse will be square root of 10 squared plus 10 squared. That comes out to be 14.142 inches. And then the final length of AB. Oh, we can do that. That's the orange triangle. So I need this side 9.7 and this side 10.2. So here's the final length of AB, square root of 9.7 squared plus 10.2 squared. That is a slightly different number, 14.075 inches. Notice how I kept a lot more than 3 sig figs on those. I'm going to subtract them. And so all of these digits out here, they just disappear when you subtract them. So since the length change is so small, you need a lot of decimals. In fact, I probably should keep up a couple more decimals. I did in my calculator. So now if I want to find the strain in AB, what I need is delta L for AB divided by L initial for AB. Well, the L initial for AB, that's 14.142 inches. And now delta, that's the final length, 14.075. Minus the original length, 14.142, and those are both inches. So we subtract and divide, and we get, if we kept enough precision in our calculator, minus 0.00469, dimensionless. Notice all these strains are dimensionless. I'm not putting pascals or psi or anything after them, dimensionless. What does the negative mean? It means that side got shorter. This may not be one that you can visualize, but apparently, because of the change in shape, this line actually ends up a little bit shorter. You saw that it was a little shorter, right? 0.075 instead of 0.142. So that's why you get a negative. All right, let's do AC, the normal strain in AC. Well, we need the change in length of AC divided by the original length of AC. Where's AC? AC goes from here to here. So originally it was 10 inches plus 10 inches. And then the new length is going to be add 0.2 at the top and add 0.2 at the bottom. So to get this one, my change in length would be 0.2 plus 0.2, 0.4 inches longer that it got, and my original length was 20 inches. So divide those and you get 0.02 exactly, or if you want to make it 3 sig figs, add 2 more zeros. And finally, the strain in BD, that's also the change in length of BD divided by the original length of BD. Where's the change in length? Well, it started out as 10 plus 10, that's 20 inches long, and it got shorter by 0.3 inches on each end. So the change in length for this one is minus 0.6 inches, and the original length is 20 inches. So multiplying that out, you get minus 0.03. 2 more zeros makes it 3 sig figs. And we're done. That one's negative because it definitely got shorter. All right, one more example. So here we have a rectangle of material and it's getting stretched out so that it gets a little bit wider, 0.02 inches on each side, and a little bit shorter, 0.01 inch at the top. And what the problem asks us to do is we're supposed to find gamma relative to an xy coordinate system right here, and also gamma relative to an x prime y prime coordinate system right there. Let's start with xy. So using xy coordinates, what happens? Well, the original angle is 90 degrees right there. And can you see how if you take those two coordinates, this one just got a little bit shorter? So now our new coordinates are right here. Can you see that that angle did not change at all? With respect to the xy coordinates, we weren't really shearing it that way. We weren't tending to cause it to do that. We just squished it that way and stretched it this way, and so that angle stayed 90 degrees. Can draw that with a little picture. Here is point A, and the new shape is right here. It's a right angle, and we have no angle change. So that means that the new angle at A is pi over 2. So the shear strain at A is pi over 2 minus pi over 2. It's equal to 0. No shear strain as far as if you're looking at this with an xy coordinate system. What about the other one? What if we looked at this with those x prime, y prime coordinates? It seems like there must be something different going on with the x prime, y prime coordinates. This would originally have been a right angle, but now because of the deformation, this endpoint is no longer there. It's now down over there. And this endpoint's no longer up here. It's now moved down over there. So I think I'm going to have an angle change when I consider those coordinate axes. Draw a little sketch. There was my original y, there was my original x. Here's my original little rectangle, and there's point A with my x prime axis right there and my y prime axis right there. And now the new points, I said they'd move down and out. I want to make a little triangle that involves this new location. And I'll have the same thing on the other side. It also went out and down, so you would also have another little purple triangle over here. So the idea is that our original angle was 90 degrees, but we are going to have a new angle that is not 90 degrees. And I'm going to use one of those purple triangles to figure it out. My thought process here is, if I can find this little angle in here, then I might be able to figure out the angle change, or to figure out the new angle, which is what I need. So let's start by trying to find that little angle. I'll call it beta. To find beta, I'd really like to know the sides of this triangle. It looks like the bottom edge of the triangle, it was 5 inches before deformation. Now it's 5.02. And this side of the triangle was 5 inches before deformation. Now it's 4.99. So let me write those down. This side is 4.99. This side is 5.02. So the tangent of beta is the opposite, 4.99, over the adjacent, 5.02. So beta in degrees, it is 44.83 degrees. It is barely smaller than a 45-degree angle, but it did get a tiny bit smaller than a 45-degree angle. In radians, that is 0.7824 radians. But there's also going to be another beta over here. And what I really want is the new angle, theta prime. I know it's going to be pi over 2 from the middle plus these extra little bits. Or another way to think of it is, if I went all the way from here to there, that's pi. If I subtract from it 2 betas, I will get theta prime. Why don't we write it down that way? Theta prime is equal to pi minus 2 betas. And we get theta prime is 1.577 radians. So just a little bigger than pi over 2. So now let's get gamma. Gamma with respect to these x prime, y prime coordinates is not 0. It's going to be pi over 2 minus the new angle theta prime. That comes out to be minus 0.00600. So it does actually have shear strain when you rotate and view it with respect to those x prime, y prime coordinates. And we solved the problem. That's the end of my notes today on normal strain and shear strain. We've worked 3 examples to kind of practice solving them. Usually with strains, what you're trying to find are original lengths, final lengths, original angles, and final angles. So these problems tend to be a lot more geometry and trig and not so many free body diagrams.